Now we are live. Now, it's called a cloud. Mhm.
Yeah. It's good. Okay. So let's talk about conference by Julian Barraga Amado from here, from the University of Lisboa. We're talking about the effect of resummation of retarded grid structure and great body factor in ADS.
Thank you, Bruno. Well, first of all, I would like to thank Giordano and Davide for the invitation and the opportunity of presenting this job that has been done in collaboration with Shankhadeep and Arpit in India. Okay, this is the last O2 geometry of the program. So, I first of all I would like to present the metric and then the study of scalar perturbations on this particular background. Then I briefly will discuss the Trieste formula, like the connection coefficients, and then I will present just two straightforward computations that you can do with these connection coefficients. Yeah, actually, this began like when I applied for postdocs, I was rejected because they said that I was not scientifically independent from my supervisors. So then I decided to move slightly and then say, okay, I work with the Heun equation. Now I will work with the connection coefficients. And then for the case of Reisner-Nostrom ADS5, I will just present some plots because it's analogous to computation. So, and finally, I will try to conclude about the results. So the metric, the line element of a KRADS black hole is described. I mean, it describes a black hole with two independent angular momenta that are parameterized by A1 and A2 hat, and we are in ADS. So L is the radius of ADS. M is related to the mass of the black hole. And well, these two functions are just defined this way just for convenience. A1 and A2, they are bounded, so they are between 1 and 0. Well, the idea is to study scalar perturbations on this background. This is linear perturbation, so we will try to solve the Klein-Gordon equation in a fixed background, and it's a massive scalar field. So I will consider just an ansatz that will separate the radial and the angular part into two second order differential equations. But here we will mostly talk about the radial part. The angular part, I mean, you have to solve to get the separation constant, and then you need to put the separation constant into the radial part. But we will take the results from granted. Actually, in the case where we will consider, which is the equal angular momenta black hole, the separation constant reduces, so it's easier to compute. Actually, the angular part is given in terms of the hypergeometric equation, so it's easier to solve in this regime. Omega is the frequency of the mode, and M1 and M2 are related with the magnetic or the azimuthal quantum numbers. I'm not really super rigorous about the ansatz, but well, it seems just for convenience, let me just keep the notation short. So the radial equation is delta R is related with the position of the horizons, and lambda L is the separation constant that you introduce to decouple the ODEs. So we defined these dimensionless parameters and coordinates just to get rid of the radius of ADS, and the equation is essentially just dimensionless as well. So delta R is just given in terms of the roots of this sixth order polynomial, and we will consider R squared as the generic as our radial coordinate, and then the zeros of delta R are related with the position of the horizon of the black hole. There R plus tilde square is the other horizon, and then you have the inner horizon and one horizon that is purely complex negative, actually. So you have in the R tilde square, you have four regular singularities. And then we characterize, I mean, by solving the Frobenius solution near the singularities, you can compute the initial coefficients. So you get the initial or the characteristic exponents, which are given in terms of the frequency and the angular velocity and the temperature of the black hole. And at infinity, you have this usually in holography, they talk this as the conformal dimension of ADS5, which is delta, or if you want, it's just the mass of the scalar field. So now the idea is that we take this equation and we will write on the Riemann sphere and the complex plane. So we do a Morris transformation, and then we introduce this asymptotic transformation, and the equation it is of the Heun can be written just in the Heun form, where K naught and Z naught are the conformal modulus and the accessory parameters. So just to show you, Z naught is just given by the ratio between the horizons, and K naught is written in terms of the if you want this, I mean the critical exponents and the separation constant. So
Can I ask some questions? So let me try to see. Well, I see this word asymptotic transformation. What do you mean? I mean, asymptotic is you call asymptotic transformation where
this transformation, I mean, yes.
Okay. And this R is the same function that appeared in your answers.
Yes, that's the radial solution, the radial part.
So you transform them.
Yeah, now we want to solve the equation for F of Z.
Okay, so this was preliminary material to reduce the original equation to that point equation.
Yes, yes. So this is the equation that we want to solve. As I said, it has four regular singular points, and
So in which region to solve?
we will study scattering problem between the horizon, the other horizon, and infinity.
So infinity is an infinity, and the
At 1. Z equals 1.
equals zero.
Yes, yes.
is a default.
Yes, is at Z naught. So just to recap, this is the equation. Then I will do a different transformation just to put it in the normal form. This is a transformation that just removes the first derivative. So this is now the new Heun equation. It's just this is, I mean, in what they identify as the radial dictionary, the Heun equation is written in this way. So you can see that you can identify the different A's with the, if you want, with the single monodromies or the characteristic exponents, the Frobenius. And then the accessory parameter is given in terms of U. So the interesting thing is that this equation, it appears as a reduction of the BPZ equation when you consider the semi-classical limit of the Liouville theory. This is why they speak, I mean, Bonelli, Llosa, Ricci, and Tanzini, why they are interested in this radial dictionary. So just, well, I think this is more proper answer to Alec question. So we are interested in solutions that around T or Z naught and 1. So and then schematically, I mean, if you look at this, I mean, you have the 5-point function, and then you take this limit. Okay, I'm hitting a few things here. You can express the solution to the Heun equation as a semi-classical limit of the conformal blocks. And the connection coefficients, I mean, you computed them using this crossing symmetry as well. And also, I mean, you use the limit, and then you use crossing symmetry and the OPEs to compute these connection coefficients. So yeah, they essentially computed using the crossing symmetry of the CFT. And then the connection coefficients are given in terms of this M, which are like the connection coefficient of the hypergeometric. And it also involves some new ingredients, which are the derivative of this F and this A. So A is I mean, you can express A, you can call it the Floquet exponent, or you can call it the verb of scalar in the vector multiplet, or even I mean, for me, the natural name will be the composite monodromy. But an F is just the instanton part of the Nekrasov-Shatashvili free energy. So here, actually, I mean, F is also related to the classical conformal blocks, if you want. So the idea is to use these connection coefficients to compute a physical quantity. So let me just briefly discuss how are the boundary conditions that we want to impose in the problem. So we have two linearly independent solutions around Z naught. We analyze the asymptotic behavior at the horizon, and then you see this solution is an outgoing wave, but since this is a black hole problem, so we are interested in incoming wave solutions. So we set this coefficient to 0. So the radial solution is just given by this homotopic transformation, and then the Heun solution, and then we express this solution in terms of the other two, so that involves the connection coefficients. And if we do the same analysis, we write the solutions at the corresponding at the spatial infinity, or at Z equals close to 1, we know that the solution, they have two different behavior. One that is a normalizable solution, and the other that is a non-normalizable solution. And we will restrict to delta larger than 4. Actually, yes. Actually, if you want to consider massless case or delta as an integer, you need to change the prescription. You need to introduce degenerate field for the. So you need to introduce an logs in the solutions. So this is something recently done by Rangamani and Gia. So, but in this case, this is the normalizable solution, and this one is the non-normalizable. And the retarded Green's function is defined as the ratio between the normalizable and the non-normalizable, or is the ratio between the response to the source. And yeah, they are, I mean, they can be computed in terms of the connection coefficient essentially, and then you have to just to put here where this is A naught, AT, A1, and A infinity, you put the single monodromies or the thetas, the Frobenius, the initial coefficient of the Frobenius solutions. So the idea is now we need to compute F and A.
But what do you want to know about infant?
Why?
No. What do they want to know about the green function?
We were interested in computing just an asymptotic expansion in the limit where the black hole is small. So, and it actually we were interested in the gray body factor, but since this is already half of the way, so we say, okay, let's just also compute the retarded green function. So the computation of the gray body factor is a bit subtle because you can identify the boundary conditions, because when you do this scattering problem in asymptotically flat spacetimes, at infinity you have the behavior of an incoming and outgoing wave, but in ADS you don't have it anymore. You have just this decay of the solution. So we follow some works by people from here, Natario, Schiappa, well, Harman, I don't know where is he. So where they just consider different regions of the space time of the radial solution. So the radial equation simplifies. They solve it analytically, and then in an overlapping region they match the coefficients. Yeah, a far region from the horizon, a near region to the horizon. And then Noda and Motohashi, they computed using the same idea, but instead of at the horizon, they consider the Heun solutions, but for the connection coefficients, they consider just the ratio of Gaussians.
Sorry, I'm completely ignorant about this rotational thing. So, what is how the gray body factor is related to Heun equation? I mean, which quantity in Heun corresponds to gray body factor?
I would say that it's related with the Heun equation through the connection coefficients of the Heun equation. So are the connection coefficient of the solutions which will be related? Yes, it is related. It is related.
One thing correctly expressed in terms of the other, or you have to use an integral.
Yeah, I mean, I will define. So the idea was that instead of using the ratio of the Gronskians, I will use the connection coefficients provided by the formula. Yes.
How do you define that?
You define the fluxes at infinity at the horizon, then you take the ratio. You see that these fluxes, they can be expressed in terms of the connection coefficients. Yes. So yeah, this is the computation that we will do. Just the ratio between the fluxes.
Black hole is supposed to have this analogy between a black hole and a black body. This is from this hole. And then black holes with all the charges, like in this case, you have an angular velocity, doesn't really behave like a black body. It behaves more like a gray body. So you have something this. If you remember the physics, you have Stefan Boltzmann law. Mm-hmm. So it's proportional to the teaching of all, and the coefficient in front is supposed to be fixed by quantum mechanics. In gray body factors, you have some constant that's not fixed by quantum mechanics. That's an extra. This is
the gray body.
And this is historical vision. They did that in the 70s. They called gray body factors. So people from gravitation call this. But this is the classical vision. Okay.
So for the specific computation, we use, as you mentioned before, we will use the angular momentum, the equal angular momentum, and well, the separation constant is just I mean, it's related with the angular momentum quantum number of the angular part, and we also parameterize the rotation in terms of the radius of the horizon, and in the extremality condition, which means that the temperature of the black hole vanishes, we can find like a maximal rotation parameter that we introduce into the rotation, just to parameterize, just to have a more convenient form to express the rotation, where alpha is a parameter that tells you that when it's 0, you are in a non-rotating case, so you recover Schwarzschild ADS5, and when alpha is 1, you are in the extremal black hole limit. So, okay, now the idea is to compute this F. F is given by, I mean, F has a series expansion in powers of t, and is given by the mass. I mean, this is related to the instanton part of this n equals 2 SU2 supersymmetric gauge theory with 4 fundamental hypermultiplets. So since we want to obtain like just an asymptotic expansion, we will use the same. I mean, we will use the series definition of the instanton partition function, and then we replace this A by the single monodromies.
This is supposed to have coming from this Nekrasov.
Yes.
What's the really the language of this poles in A?
Well, they haven't studied the poles, but there are some works by, I think it's Gorsky, Mihailin Sopenko, and Alexeyev, and I forgot the second author. Well, they realize that if you sum up all these poles, they have to give at least the most singular ones. They will give you the branch cards of the prepotential, I think they call. So I will try to talk about the poles later. So the idea is that you solve the Maton relation to find A. So and as I said, this is just the equation that Alec showed us a few days ago. So what we do is we suppose these ansatz for the rotation. This is just for the small black holes, and we find the coefficients recursively. So you see that the poles that appear in the instanton partition function, they are translated into poles of L. And yeah, subsequently, they also appears in the derivative of the free energy. So you have these poles, and so the idea is that we will try to apply a resummation to these poles and see what happens. What are the contributions of the resummation in the computation of the gray body factors? Well, there is also another approach. If you want, you can just stop conveniently and then you don't care. I mean, if you have the pole that appears at fourth order, then you stop at third order if you want. But we compare what happens if you stop before or you consider this resummation. And for simplicity, we just focus on the S wave mode, which means that L, M1, and M2, they are 0. So, and this is, so we want to, the first thing that we want to do, we want to compute the correction to A. And so we are just solving near to the pole. So that's why this is half minus this. Here it doesn't matter if you plus or minus. And the interesting thing is that all these instanton partition functions, they start to accommodate in this way. They really accommodate. This is really nice. So, and then you can recognize that this is essentially given this is a sequence of numbers that are well, the Catalan numbers. So then you can just replace the Catalan the sequence by the generating function of the Catalan numbers, and then you can try to compute new zero. So, well, this is just the expansion of the accessory parameter for a small R tilde plus. So, yeah, as I said, I mean, we just assume that this is, I mean, all the contributions at second order, I mean, at R plus square, they fall into this sequence, and then we replace by the generating function, and we computed the correction to the VEF. And we did the same for the derivative. And then for the derivative, you see that they also rearrange in such a way that here, for example, the Catalan numbers appear again, but this one is fancier. So we went to higher order to have an idea of what will be the generating function for this. And then we found that actually the zero order is given in terms of this log.